Welcome back. In this video, we will now take a look at what are the set of response mechanisms available to you. Remember, the three pillars of operations are monitoring, which is meant for you to detect if something is wrong or what is wrong. Then observability, to help you understand and make sense of what you're detecting, why something is happening the way it is, potentially with multiple candidate answers. And then response is the pillar which tells you how to act on that information and what specific sets of actions are available to you as choices. So let's talk about performance management, which is one of the key aspects of machine learning execution in production. So some of the more common performance issues are as follows. Because each of these issues have specific reasons, they would entail specific actions that need to be done to alleviate the performance problem. So let's say, for instance, the CPU or the GPU is the bottleneck in a specific execution. Then the bottleneck nature, the root cause of the bottleneck could be because the computation itself is not optimized. Either it's a very slow matrix operation when you can actually make it much faster by using some pruning techniques, for instance, or the model itself is too large for the available resource. So the classic example here is you run like a CNN model on a CPU, right? In which case the model being too large means that the time it takes for classifying an image or processing an image becomes that much more. Memory being an issue or memory being a bottleneck usually comes about because you either have a significant amount of overhead associated with loading data into memory, and that could be because your pipeline is expecting a chunk of data to be available together, or it could be because the weights associated with the model is too large compared to the available memory that's there with you, or it could be because there is no batching at all, and therefore for every single element of data that needs to be predicted or scored or inferred, you're setting up certain resources like network sockets or strings, for instance, and then you're not really reclaiming that space fast enough. So then it keeps adding to the pressure on the memory itself. Disk I/O as a resource could be a bottleneck in certain situations, and that could be when the model is read from the disk for the first time. Usually that happens when you bootstrap a machine learning system in production, especially a deep learning model. Or it could be the case that the input files which are required for setting up the model for the first time is actually quite large in size. So that's with respect to disk. Network bottlenecks can happen when you've got a significant payload because the input data set for the request itself is comprised of multiple different, let's say, dimensions of data, and each of it has multiple kilobytes or megabytes of specifications, in which case all of that payload needs to go across the network to reach that particular HTTP request, HTTP service, right? So that payload information itself needs to be transmitted. So therefore, network becomes the bottleneck for that duration. Or it could be the case that data is not serializable, or its serialization formats are inefficient. And then last but not the least, the code or the logic could be a bottleneck. But it manifests as resource bottlenecks in some way. But the code or the logic itself could be a bottleneck, in which case the specific problem could be that the operations that you perform are not really optimal, or you use frameworks or libraries which are deprecated, and therefore those specific operations that you're dependent on them for are not optimal anymore. So the crux of the matter is that don't guess as to what the root cause of a performance problem is. Instead, always measure, and the measurement you do will be critically dependent on the kind of matrices you have access to, the observability data, etc. The other practical thing that you have to keep in mind is at any point in time, the bottleneck can be one of these resources, but over a period of time, as the machine learning model executes in production, the bottlenecks are likely to shift and not remain in one place for a long time. So if you take a specific deep learning model as an example that you load up for the first time, let's say an LLM, right? Or a foundational model that you bring in from Claude or Anthropic, rather Claude type of model from Anthropic or, OpenAI models. So the model, for the first time when you load it up, it's going to go through a significant amount of network or disk IO bottlenecks, right? It'll manifest that way because it's actually busy spending all the time loading the data. And the moment that's come in, then that amount of memory that's required for keeping that model and model available will start to become the bottleneck, right? And that will also manifest as CPU bottleneck because each time you want to load additional elements of data to score on, the CPU will need to do a context switch for those data elements to either be flushed into disk because the memory is already getting pressurized by the model's largeness, right? So it what I'm trying to say is basically a typical model execution in production will go through a sequence of these bottlenecks across these resources. It's not just going to be one resource bottleneck throughout the lifetime. So when you optimize, you've got to go back and measure, obviously, but then you look at the total end time of a specific model response and break it down into stages and see which stage is most important for you to optimize. Okay, so what techniques are available for optimizing? Obviously, the default caveat for all of what I'm going to say in next few minutes is the specific techniques will be very specific to the code that you've written and the infrastructure that you're using for executing that code. So there is no foolproof general purpose technique that's available that will work in under all circumstances. That's why many people think about performance optimization as a science unto itself. But the crucial part is it's not an art. It's very much a science, which means that you can measure, and what you measure is what you're going to get an insight from, and what you get an insight from allows you to act in specific ways. So it's in fact, it's as analytical as you want it to be. Okay, so what techniques are available? I'm just going to give you like a handbook of techniques, which are broadly generally applicable in many different scenarios of machine learning usage. So first, at the level of model optimization, which means what can you do in the code itself? First up, you can do something called as quantization. You'll find that most floating point number or arithmetic is by default using 32 32-bit representations. While that's great for precision, you'll find that for most deep learning use cases, 32-bit is too much precision. In fact, 8 bits work perfectly fine. But more importantly, the difference between 32 versus 8 bits is 4 times the size. And that 4 times the size means you've got 4 times lesser amount of data that can fit into the cache line, the L2 cache line in the GPU, which means that that much lesser amount of data gets processed in one iteration if you use a 32-bit representation. So it's got a cascading set of impacts on multiple different things, but mainly performance. So if you can get away with quantizing the data, converting it from floating points to the closest integer, which is 8 bits, that's better for you. Pruning is another interesting general purpose optimization technique. So here, especially suitable for deep learning models, if you've got too many interconnected weights, loading the weights, tracking the weights, training the weights, and then scoring using those weights can be a significant challenge. Obviously, at the training stage, you do some amount of pruning because that's dependent on the input data that you train on. But once you've arrived at the final model that you want to promote to production, you can go through a pruning exercise, which will remove some of the unnecessary weights, making it much, much smaller in terms of cross connections between the layers. Distillation is the other angle where you are now not removing unnecessary weights only because the pruning step typically does not reduce the accuracy because you're just removing unnecessary weights with weights which are lesser than the threshold. Whereas in distillation, you're actually creating a smaller model en masse by mimicking the performance of a bigger one. So case in point, it is commonly believed, or maybe it's already been discussed academically as well, that the DeepSeek model um, that was actually created using distillation on top of the OpenAI models, right? So, which means they use the OpenAI models outputs as like supervised data for the smaller models that DeepSeek was building to arrive at the same type of accuracy or same level of accuracy. And then with further optimizations, it became even better for certain types of tasks. So distillation is actually quite a powerful technique. And then you have specific graph optimization approaches that you can take up. So this is actually slightly more advanced for this course. But if you're interested in this, maybe you're taking the deep learning course, in which case you can go take a look at these techniques separately. Okay. Now, what can you do beyond changes to the model itself or model architecture? One very useful, simple, general purpose technique is to batch data together. By batching, I don't really mean taking thousands of samples and feeding them together instead of scoring every sample by itself, but take up small groups of samples. Like for instance, if you're doing an image classification problem and you now have to predict the new, for the new image that's coming, instead of predicting one image at a time, you can potentially predict, let's say, 16 images if it's available to you together. So that makes it slightly more efficient. Hardware acceleration, always an option, but always also expensive. So GPUs, TPUs, edge accelerations, if you're doing a lot of inferencing at the edge, being able to use something like Jetson is quite useful. Then efficient serving techniques can also help in improving performance. So this is after the model is trained and built. So you can use dedicated inference servers, which are dependent on the type of algorithm or the type of library that you use. Like TS serving is one example. NVIDIA's Triton server is also another example. Or you can also have mechanisms of, loading the model once as part of bootstrapping and then having it warm so that you're avoiding the need to keep loading or keep having cold starts every time you want to use the model. So if you remember, some of you might have taken the big data course, and there we spoke about the Apache Arrow bindings available for writing custom Python functions. And then user-defined functions like that can be used for loading heavy deep learning models once at the time of setup, and then use it repeatedly for every single inference after that. So that's one technique available within the big data world for keeping models warm and then serving it using the models that are there in memory. So what are the deployment tricks are available? So what we spoke about so far is, code organizing tricks, right? Either at the model level or at the pipeline level, right? Or at the hardware level. Now, when you start looking at ways in which you can optimize at the deployment level, once all these steps are done, asynchronous I/O is always a fantastic tool that's available to you. So instead of synchronously waiting and then blocking on the resources which have been utilized, you release those resources and then say, hey, come back and take a look at the output once it's ready. So that way of execution is always faster, especially when you have very high, throughput requirements. Preload models in memory, so always a good option. So this you can do at the deployment time as well. Limit the extent of concurrency so that you're not getting overloaded with concurrent requests. So the analogy here is, let's say there's a event that's happening. Let's say there's a cricket match that's happening in IPL, or like there's a famous music concert like the Coldplay concert that happened in Bombay, in Mumbai. So you have finite resources. Those finite resources are fundamentally better off focusing on the main functionality. Like for instance, the Coldplay band singing is the main functionality, right? Or the cricket match is the main functionality. But if you've got the crowd for the concert coming in being so large that it requires, extra security, extra people to handle that crowd, extra food, extra drinks, blah, 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 much beyond capacity, much beyond what is available, then the resources that will typically be spending time making the concert a success or the cricket match a success will end up spending all of that energy in controlling the crowd itself in the first place. Like even before the crowd is probably entered into the stadium or entered into the concert hall. And that's a waste of time. That's a waste of resource. So what you then do is you limit the extent of concurrency that's there at any point in time. And then you focus all your energies on making sure that those who have already been, begun their serving journey get through it as fast as possible. Which means, if you go back to the analogy, the cricket match has started and there's still a huge crowd that's waiting. Instead of allowing all of that crowd in and then spoiling the entire experience, wasting your energy managing the crowd, focus on the crowd that's already inside, making sure that they have a good experience. And as and when they make a move, or let's say some of them have to leave for whatever reason, then you trickle feed the crowd from outside. So this way, you can do concurrency control outside the perimeter of the critical resources which are handling the core functionality. So this avoids unnecessary contention at the model layer. And if you extend this even further, right? If you extend this even further and take it all the way to the edge, which means all the way to the origin of that kind of demand, then you can use something called as content distribution networks or CDNs, or in other words, edge computing, and make for even faster access to the models. So if you think about IPL, and the analogy here continues with cricket, in IPL, the core stadium is what is offering the core experience. So let's say, for instance, the Hyderabad stadium is offering the experience of watching Sunrisers Hyderabad participate. Now, obviously, the experience is expensive for the typical population in the country, and also the number of seats are limited. The crowd always is going to be much higher than what is capable to be handled by the entry guards. So what IPL or BCCI has done is taken that feed, recreated a smaller experience in many different satellite towns, which are tier 2, tier 3 towns, so that those people in those towns need not travel to a city like Hyderabad only to experience what the combined viewing experience can look like for SRH fans, right? So that's an example of taking the load and creating a version that can run at the edge. It may not be the same experience, like it may not have the same model accuracy or efficiency or recall rates, etc. But it's good enough to meet the demand. It's good enough to solve a problem. So that kind of a model is what's called as an edge computing. CDNs are a related concept which make the availability of models or content at the edge, at the local level, easier, so that everybody does not need to talk to a central server. Furthermore, beyond these general purpose optimizations, there are also specific optimizations available within GCP and within GKE. So one example is at the level of the image itself for Kubernetes environments which are managed by GKE, you can use ways of minimizing the impact of those images on the resource utilization by using slim versions of Python images. So let's say, for instance, in your Docker file, if you remember from the previous week, you just specified Python 3.10, 3.11, etc. That includes the entire set of libraries that ship with a typical Python distribution. Maybe for your use cases for a machine learning, half of those libraries are useless, in which case you can use a slim distribution and then use the requirements file to bring in only those libraries that are of interest. So that's an example. You can also preload and warm up the models during container setup. So that's a version of the optimization that we already spoke about. So instead of doing it in the code, you can do that warm up in the container, right? So that's something that's useful. And then you can also think about pruning out dependencies which are not useful for you. So at the Docker level itself, you can use multi-stage builds as a way to deal with multiple dependencies, such that only the absolutely necessary dependencies are being brought in. Furthermore, At the pod level also, there are optimizations that are possible. Batching of requests, like that's just a version of the batching the problem that we saw before. Instead of doing it at the code now or the inference server, you now do it at the pod level. Second, CPU throttling is something that will always create a problem because you're allowing too many requests to come in. So therefore, in these kinds of scenarios, enable autoscaling, right? If you enable autoscaling, then the extent of CPU throttling might be controllable because you now have new pods being spun up. So what is autoscaling? Autoscaling is when, based on certain matrices, you allow GKE to automatically scale up the cluster by adding more pods and more nodes. That's what autoscaling refers to. The matrices that are of interest could be CPU or memory. Typically, those are the main ones that are of interest. So if you find, for instance, the CPU utilization is consistently high in a pod and the available pods are all behaving the same way, then GKE can interpret it as there isn't enough room for servicing more requests using the same cluster resources. So let me go grab some more nodes, spin up some more pods, and have more resources available for further execution so that my overall throughput increases. So that's what autoscaling is. It's very powerful. Obviously, it involves an expansion in cost, which might be problematic for some people. So you can limit the extent of scaling by having configuration parameters. So we'll see an example of this in the hands-on session. You can also ensure that pods use GPUs, and those GPU using pods are only deployed on GPU nodes. So that's a pod level mapping that can happen because that's very useful for ensuring that the right efficient utilization of resources happen correctly. Persistent volumes are a great way to make sure that large models which have been loaded up by pods remain accessible even if the pod were to be shut down because of various reasons. Then finally, rolling updates are a great way to get models warm in different pods as the pods go through their own life cycles. So some of these optimizations are potentially advanced for this course, but I'm just mentioning this here because you should think about it as layers at which the optimizations are possible. Some of them are general purpose, some of them are more specific to the infrastructure choices that you make. So the autoscaling example that I just talked about, here's how you would specify this in a configuration file. It's a YAML file. You would, for instance, say that CPU is the metric that's of interest for you. And within CPU, you're interested in the utilization. So if the average utilization is 70% or more, then it triggers this autoscaling pipeline. And the autoscaling pipeline here might define that go from anywhere from 2 replicas to 10 replicas, right? So that if I'm at 2 right now, and the CPU utilization on an average has been 70% for the last, some period of time, then GKE decides that, okay, it's time to spin up another pod, and then a new pod gets spun up with a copy of that particular model. Okay. So I'll take a pause here, and in the next video, we're going to take a look at one of the most mundane of activities that's in the realm of machine learning, and that's logging. But let me try to make it interesting for you. So let's meet again.